This video is for entertainment purposes only. Over here, we are going to learn about flammability diagram. Flammability diagram. What are its uses? So, flammability diagram, it is used to justify the inerting limit, and it is also used for tank entry purposes. It forms the basis of controlling gas ring operations, and also it's a very good explanation, like if someone wants to know why inerting below 8% oxygen is recommended by IMO, and is also the primary control against tank explosions. So we'll start here with the diagram. We can see on the x-axis we have got blue. On the x-axis here we have got the hydrocarbon gas percentage by volume, which is measured by tank scope. Okay, then over here on our x-axis we can see it is oxygen percentage by volume. So oxygen percentage by volume, it can be found out by the use of oxygen analyzer, right? Over here we'll just call it on this axis we see this line from extending from A to B. What is this line? This line is a graphical representation of, in the atmosphere, in the air, the oxygen is 21%, right? So for 21% oxygen, the remaining is other concentration, is other mixture of the gases. So inside the tank, when the air is there, 21% of oxygen is there, the rest all gases, the mixture, we'll just call it hydrocarbon mixture, right? So if we reduce, if the oxygen is 21%, 20.9% over there in the tank, what is the rest? The rest is the hydrocarbon mixture, right? So we start from here. Now we see, as we try to decrease the oxygen content, what will increase? Something has to replace that oxygen. That will be the hydrocarbon mixture or the inert gas. So as we induce or put inert gas inside the tank, the oxygen level will go down, right? The hydrocarbon or the inerting mixture, which is the mixture of all these gases, inert gas is majorly a mixture of nitrogen and carbon dioxide, so that will increase little bit here. Then we decrease the oxygen concentration more, somewhere over here. If we plot the mixture of hydrocarbon, that will be somewhere over here. If we decrease it more, somewhere over here, and we plot the hydrocarbon against it, it will be somewhere over here. If we decrease more oxygen, say 16%, the remaining will be this mixture. So that's why we see this line over here is slant. It's not exactly straight. Now over this line, which is the mixture of hydrocarbons and the inert gas, every mixture, every product has its own lower flammable limit and upper flammable limit. So there will be a mixture of hydrocarbon gases from that product. This point C, we call it lower flammable limit, and this point D, we call it upper flammable limit. This lower flammable limit and the upper flammable limit can be obtained from the MSDS of that particular product which we have. And the lower flammable limit and upper flammable limit, it is measured using the instrument which is known as explosimeter. Explosimeter is the name of that instrument, tank scope, and this, right? So for every product has its own LFL and UFL. Because LFL and UFL will depend upon the product, it forms the basis of this flammable mixture. So every product will have its own flammability diagram. One diagram cannot be used like for each and every product. It's gonna be different because the lower flammable limit and the upper flammable limit are different. So as we slide this line, we can call it like, the line AB or the Z axis, I don't know, whatsoever you want to call it. We slide it, we bring it to, for example, say here somewhere 19%, it will come over here. So together with this thing at 19%, the LFL will change, and same for the 19%, the upper flammable limit will also change. When we bring it to 15%, the lower flammable limit, it is going to change, and the upper flammable limit, it will also change. So we keep on dragging this line over here, reducing the oxygen concentration, and then at one particular oxygen concentration, we will see the line of upper flammable limit and the line of lower flammable limit matching. Lower flammable limit is coming over here, the upper flammable limit is coming over here, it is matching. And this concentration of oxygen, we see here, right? We can extend it to further, make a difference. What do we call that? We call it limiting oxygen concentration, the line of control. Limiting oxygen concentration. So limiting oxygen concentration is the oxygen concentration at which flame will not occur, irrespective of the hydrocarbon mixture, irrespective of the amount of hydrocarbon inside the mixture. We see here like what it is, maybe 11%, example, approx. Okay, so at 11% of oxygen, do we see this flammable mixture envelope extending beyond it? No. So that means beyond this point, no flame can happen. Okay. If the flame doesn't occur, no risk of explosion, the fire triangle will not be completed. You have the oxygen, you have the hydrocarbon, but flame will not occur. At this particular oxygen level, if you want to reduce the hydrocarbon, not a problem. If you want to increase the hydrocarbon, not a problem. You keep on increasing the hydrocarbon level as much as you want. You go to maximum also, not a problem. Flame will not come. There is no risk of explosion. So hence it is known as limiting oxygen concentration. Now, let's see what else remains. Yeah, so anything which is below this lower flammable limit, this area is called, over here it is two-lane mixture. It's non-flammable. This mixture is non-flammable. It is two-lane. Why it is called two-lane? Because in this particular zone, if you see, no matter how much oxygen you increase or decrease, the amount of hydrocarbon is so low that it cannot start fire. Hence, it is called, this area over here, it is too lean and it is non-flammable. However, the part which is above this area, like this one, this area is called too rich area, which is non-flammable, which is also non-flammable. Over here, the percentage of hydrocarbon in the mixture is very high, but still no use. Oxygen amount is less to start the fire. So too rich or too lean, it is set in contrast with the amount of hydrocarbon concentration inside the mixture. If the hydrocarbon concentration is less, that mixture is called too lean. If the hydrocarbon concentration in the mixture is too more, then that mixture is called too rich, right? Okay, so now we see what happens. IMO says, IMO is got the recommendation for the oxygen is, it should be less than somewhere, they say 11%. Okay, we are almost already at 11%. So